Hello. Today we will continue our discussion of the electromagnetism. We were talking of the left-hand and right-hand rule of Fleming's and how using that we can determine the various directions. Today we will do something which has got related to the electromagnetic induction phenomenon by Faraday and also the concept of Lenz's law. First of all, I am drawing this structure. So say on the left hand side I have got a cylindrical material, maybe it's made up of paper or maybe wood, and around that cylindrical material I have got some sort of electrical conductor which is coiled in this manner, and it is connected or attached to a galvanometer. So this is a galvanometer, and towards the right hand side here I have a permanent magnet whose north pole is facing the cylindrical solenoid initially. So basically this has now become a solenoid. So now we will be studying the phenomenon of electromagnetic induction. So what does that phenomena says? The phenomena says that any change in magnetic field will also induce an electric field, that is an EMF. So let me write it down here. A changing magnetic field induces an electric field which in turn induces an EMF. So in the book you might find that they have directly said that a change in magnetic field will cause it induction of EMF, but actually it induces an electric field first, which in turn leads to the induction or the induced EMF being produced. So how is that induced EMF produced? What is the experimental observation? So first, when this magnet here, it is at rest, that is V equal to 0, and this solenoid here is also at rest, in that situation there is no deflection in the galvanometer, which means there is no induced EMF getting produced. But now suppose this permanent magnet is being moved with a velocity v towards the solenoid still being at rest. In this case we find there is a deflection in the galvanometer, and what will be the direction of the deflection? We will determine that shortly, but for the moment let us assume that it is deflecting towards the right hand side. It is also observed that now instead of taking the magnet towards the solenoid, if I take it away from the solenoid, even in that case there is an induced EMF in this solenoid, but now the direction of deflection in the galvanometer will be opposite to the first case. So in the first case, when the magnet was being brought towards the coil, if the deflection is to the right hand side, say, then now when I am taking the magnet away from the coil, the deflection is towards the left hand side. Similarly, instead of bringing the north pole of the magnet, if I bring the south pole of the magnet towards the coil, then the deflection will exactly be opposite in nature to what happened during the north pole. So now when I take the south pole of the magnet away, the deflection will be towards the right. So that means the polarity is mattering, and what else is mattering here? Whether I am bringing the magnet towards or away, that is also mattering. And we have noticed another thing, that when both of them were at rest, nothing was happening. I will add another thing here, that instead of being at rest, say this entire solenoid setup along with the galvanometer is also moving with a velocity v to the right, when the magnet is also moving with a velocity v to the right. So during such a situation, what do you think? Will there be a deflection in the galvanometer? The answer is no. So that brings us to our next point, the point that I am trying to establish here, that whenever there is this induced EMF occurring, there has to be a relative motion. There has to be a relative motion between the coil in which this EMF is getting induced and the magnet. It may happen that both of them are at rest. In that case there will be no induced EMF. But if it again so happens that both of them are moving with the same speed in the same direction, then also there will be no induced EMF, because we know this from our lower classes that if two bodies are moving with same speed in same direction, then their relative velocity, that is equal to 0. So there has to be a relative motion, that is important. One must be moving with respect to another. That is the important thing here. It may happen that if one is moving at velocity v and the other is moving at velocity u, that is not a problem, because now when you do the relative velocity, it is v minus u, which is not 0. So in this case there will be induced EMF. But if both of them move at the same speed, since there is no relative motion, there will be no induced EMF. Let us try to find out that how will we determine in this kind of problems whether the galvanometer will deflect to the right or left, or like how does bringing the north pole towards the magnet or south pole towards the magnet affect the situation. So this is my initial setup, and I have a permanent magnet whose north pole I am bringing towards the magnet. So what will happen when I try to bring this north pole of the magnet towards this solenoid? Well, here we will use what is called Lenz's law, and this is a very important law because this will tell us the direction. Lenz's law states that the direction of induced EMF in this solenoid or in this coil will be such that it will tend to oppose the cause which produces it. So the direction of induced EMF will be such that it will tend to oppose the cause which produces it. So here the induced EMF in the coil is being produced by this magnet which is moving. So according to Lenz's law, therefore, the induced EMF in the coil should be in such a direction that it will oppose this magnet. So when does a magnet get opposed by another magnet? When their like poles are facing each other, because we know like poles repel. So therefore the current direction in this side of the coil should be such as if it's like the north pole. Now this is something we had studied previously, that if you have a circular coil like this, then we can say that a certain pole is the north pole if the direction of current is like this. That is to say, if the direction of current is anti-clockwise. That means in this direction, the direction of current should be anti-clockwise. So you can do one thing, you can place your eye here and try to visualize what will be the direction of current. So when you place your eye here, what will you see? You will see the circular cylinder in the center, and there is this wire that is coming from the left and wrapping it, and it will act as the north pole. So in this coil, direction of current will be anti-clockwise. So it means current will be coming down like this. So once you have established that, now in the other coils it becomes easier. So this will be the direction of current in the entire setup, and if this is the north pole, this has to be the south pole. And so we see that in the galvanometer, the current is entering from the right hand side and leaving from the left hand side, so the galvanometer will deflect to the left. So from the galvanometer deflection also we can determine the direction of current. So if this is a galvanometer, if it deflects to left, that means current is entering from right and leaving from left. And if there is a galvanometer where deflection is happening to the right, that means current is entering from left and leaving from right. And current will always enter in such a manner that from the direction of deflection of galvanometer we can find out that from which side the current is entering and from which side the current is leaving, and whether a certain pole is north or south. For that, first of all, we have to determine that according to Lenz's law, whatever is the opposition happening. So instead of north pole, if here I had the south pole, then according to Lenz's law, since it had to oppose, so in that case this couldn't have been north pole, this would also be south pole then. So then the direction of current would have been clockwise, that is moving up, and in that case the deflection in galvanometer would be like this. So that we have to determine first. Let us consider a second case. So now, once again I have a solenoid with a coil wound around it, and there's a permanent magnet, but instead of taking it towards the coil, now I am taking it away from the coil. So now what will happen? According to Lenz's law, the induced EMF will be such that it will tend to oppose the cause which produces it. So here when I am taking the magnet away, how can the induced EMF oppose it? By attracting the magnet towards itself. That is the opposition, because I am taking it away. So therefore now this side should act as the south pole, because then unlike poles will attract each other and the action of me taking away the magnet will be opposed. So that means now the direction of current in this side, if you imagine it, the wire being wound like this, the direction of current should be clockwise, because we know this thing. So therefore the direction of current will be clockwise. So the galvanometer, that will deflect towards the right hand side. So by this method you can determine the direction of current. One additional point that I would like to say is that you might get problems where the magnet is completely at rest. There is no motion in the magnet, but the coil is moving. And that is a valid problem as well, because as I said, it's not necessary that it is always the magnet which has to move. What is necessary is that there has to be a relative motion between the two. So it might happen the magnet is completely at rest and the coil is being moved towards the left with a velocity v. So apply Lenz's law. You are taking the coil away, so it will be opposed. So there has to be attraction. So this side will act as south pole. So direction of current will be clockwise, and the galvanometer will deflect to the right. So either of these is possible. Now the question comes that whenever this kind of electromagnetic induction takes place, is it a violation of the law of conservation of energy? Is it a violation of the law of conservation of energy? That might be a question that is asked. Well, the answer is no. Then how is these coils which are wound around the solenoid getting this induced EMF? How are they getting that? Because whenever EMF is getting induced, it basically means there is some form of electrical energy. So where are they getting the electrical energy from? So the answer to that question is that the electrical energy comes from our mechanical energy. So whenever we, the users, are either moving the magnet or the coil towards each other or away from each other, we are doing some work on it. So we are using mechanical energy that is getting stored in the coil as electrical energy. So it's not a violation of conservation of energy. Basically the mechanical energy is getting converted to electrical energy. So the question that now may be asked is that what is the exact mechanism by which this kind of an EMF is getting induced in the coils. So let me consider a coil which has got only one single turn. So say this is the coil, and near this coil I place a magnet. Say this is the north pole of the magnet. Now whether or not we can see it, because magnetic field lines are invisible, it is true that there will be these field lines. They are always present even though we can't see them. They come out from the north pole and they go and terminate back at the south pole. So when the magnet is at a certain distance away, there are this many field lines which are interacting with the coil. Now if I bring the magnet say closer, if I am moving it, then the number of field lines which are intersecting a certain cross-sectional area, that increases. So this number of field lines divided by unit area of cross section, this is called phi b, which is magnetic flux. So this quantity is called magnetic flux. It is the number of magnetic field lines per unit area of cross section of the coil. That's magnetic flux. So whenever there is a relative motion between the coil and the magnet, mind you, relative motion, any one of them can move. So what happens during such relative motion is that there is a change in the magnetic flux with a change in time, del phi b by del t, and minus of this is equal to the induced EMF epsilon. This expression that I have just written, this is what we obtain from what is called the Faraday's law of electromagnetic induction. So according to Faraday's law of electromagnetic induction, we can therefore say that whenever there is a change in the magnetic flux, that is linked with a coil, an EMF will be induced. So there has to be a delta phi b. There has to be a change. Just having phi b doesn't matter. এখানে একটা magnetic flux আছে, which is say, because it is number of field lines per unit area, so maybe it's 100. That doesn't matter. It is 100. Within, after some time interval, it has to become say 90 or say 110 or something, so that there is a delta, there's a change in phi. And this induced EMF epsilon, this will last only as long as there's a change in the flux. The moment there is no change in flux, the EMF will cease to exist. So that's why the motion part is so important. And finally, the magnitude of this induced EMF epsilon, it is directly proportional to the rate of change of the magnetic flux. So better to say, instead of equal, proportional. And rate of change means we are dividing it by time. Rate of change always has to be with respect to time, as in this case. So if the rate of change remains steady, a steady EMF is induced. If it so happens that the rate of change is again changing, then the EMF that is induced, that will not be having a steady value. Even that will be flexible and variable. So this is very important. The first point, as we see, it says that the change in the magnetic flux can only sustain a change in the EMF. If a flux is not changing, EMF will not be induced. So if I go back to a previous problem here, like in this case, say for example I take a coil like this, and there's a magnet here which I am bringing towards the coil. Now suppose I am bringing it in, and there comes a moment when the entire permanent magnet is within the coil. So now the entire magnet is within the coil, so all the field lines of the magnet, they are intersecting with the coil. But because the magnet is at rest with respect to the coil, because there is no change in flux, the change in flux is 0. As a result, there will be no EMF induced, and the galvanometer pin, it will show no deflection. So even though the entire magnet is within the coil, the maximum number of field lines are intersecting or interacting with the coil, then also the EMF induced will be 0. So there has to be a change in flux. That is very important. If the flux doesn't change, the induced EMF will cease to exist. And as we saw in the problems above, the direction of the induced EMF, we can calculate it using Lenz's law. One final thing that we will discuss is the distinction or the comparison between AC and DC current. So AC stands for alternating current and DC stands for direct current. One of the difference between them is that this AC current, it changes its direction periodically. So if you have, say, an AC current of frequency 60 Hz, it basically means that the current changes its direction every 1/60 of a second. So it is flowing, say, from left to right for 1/120th of a second, and then from right back to left for the next 1/120th of a second. So that is what the frequency means. Whereas DC current, it always flows in a fixed direction. It has a fixed positive and a fixed negative terminal. So you will find that there are certain differences between direct and alternating current which have been given in your book. So try to go through that. And this is our discussion on Faraday's laws of electromagnetic induction. Thank you.